I mean, great. Okay, welcome everyone to this week's session. We've got the pleasure this week of welcoming Adela DePavia from University of Chicago. And she's actually affiliated with IFDS there because her advisors are Lorenzo Orecchia and Becca, who we all know Becca very well here. Been on the faculty here till 2018. So Adela is finishing up her PhD in computational applied math. She recently was awarded a Schmidt AI in Science postdoctoral fellowship, which she's going to take up at UC San Diego, I guess in the fall, right? Okay, and as you'll find out today, she's interested in optimization algorithms for machine learning, trying to improve the convergence rate and the practical performance and all that stuff. And she's currently supported by an NSF Graduate Research Fellowship, which is great, and a GEM PhD Fellowship sponsored by Lawrence Livermore National Lab. So it's my pleasure to welcome Adela.
Hi, nice to meet you all. And for anybody on Zoom, please feel free to interrupt us at any point if you have any audio or visual issues or if you have any questions. So I'm really excited to share this work with you guys. Today we'll take a look at some adaptive optimization algorithms, and we'll see some examples that might be familiar to you, or maybe even algorithms that you've used in your own work. And then we'll take a look at the sometimes surprising sensitivity that these very popular algorithms can have to even very simple rotations. So let's see. So Steve already mentioned that I'm co-advised by Becca, who you guys know. And then the work in this talk was also done with Becca's former postdoc, Vasilis, who's now faculty at the other UW. And some follow-up work with two great master students, Rick and Jose, who I think are planning to start PhD programs next year. So very excited for that. Okay. So when we talk about the surprising success of deep learning, some people might say, on many different levels, each time we have an example of success, we're seeing three ingredients work well together. So first, we have some kind of structure in our training data. And there could be lots of different kinds of structure that we can think about. But today I'm going to be thinking about, in particular, like low intrinsic dimension or manifold structure in our training data. Then we have some kind of neural network architecture that we define. So whenever we define a neural network, we define some forward map, and there are certain functional properties that result from this choice. And then third, we have our optimization algorithms that we use to actually carry out the training. So these optimization algorithms decide what path through the loss landscape we take, and they pick some potentially local minimum or stationary point that gives us our final trained neural network. So if we want to understand how or when deep learning is successful, we need to keep each of these different elements in mind. So today, I want to start by fixing our data and our architecture and just looking at the impact that different optimization algorithms can have. So let's define a concrete setting to do this in. I want to think about training a neural network to perform binary classification. So we have a fairly simple setup, like the data that I'm going to be thinking about lives in 2 dimensions. So here I'm plotting our feature vectors in literally x1 and x2 coordinates. They come from some mixture of Gaussians, and they have either labels +1 or -1. So here I've labeled, like all of our blue dots have label -1, all of our red dots have label +1. And maybe you can visually see like how you might try to draw a boundary to separate these two labeled groups. Then the architecture that we're going to think about is a 2-layer ReLU network. So if you're familiar with like a ReLU network, what we'll do is we'll take a piece of input data, we'll pass it through a linear transformation with a weight matrix W that we'll call like our first layer or our hidden weights. Then we'll apply an element-wise nonlinearity, which in our case will be the ReLU function. And then to create a scalar valued output, we'll take an inner product with a final weight layer, final layer weights that I'll denote A. And to simplify my analysis, I'm going to consider settings where this final layer weight vector is fixed and random. So you can think about them as like Rademacher IID, random variables. So when we do our training, the only parameters that we're actually optimizing over are our first layer weights. So To train this neural network, we're going to minimize the expected linear correlation loss. So here I'm going to ignore the effects of finite sample size, and I'll think about the loss that we incur in expectation over XY samples that are drawn from this like mixture of Gaussians that we've defined. So in this setting, let's compare the decision boundaries that we learn when we train with different optimizers. So here I've trained with 3 different methods: gradient descent, atoms, and GD. And what I'm plotting is the decision boundaries that these algorithms learn. So for example, for gradient descent learns this decision boundary. And what this means is that everything on the right-hand side of this pink line, gradient descent is assigning positive label to this side. And then everything on the left, gradient descent is assigning negative label. So this seems like a fairly reasonable rule. Like it mostly separates the red and the blue. It might be a little bit hard to see, but there are some, like this data is not linearly separable. So there are some like misclassified points, but largely this seems reasonable. Since we know the underlying data distribution, I can actually compute the Bayes optimal decision boundary for this problem. So this is the decision boundary that probably minimizes the probability of misclassification. And I've plotted it here in dashed green. So we can see that, while gradient descent learns this reasonable linear boundary, the optimal boundary is actually something different. And in particular, it's something non-linear. So one interesting observation that this research group made recently was that while gradient descent is kind of doomed to provably learn a linear boundary for this problem, Adam and a related method called SignGD both converge to a provably non-linear boundary. So that's what we're seeing here, this like a V-shaped boundary. And so this was an exciting observation because one argument was like, maybe this is part of the success of like Adam compared to gradient descent. Maybe it has the capacity to learn quote unquote richer nonlinear decision boundaries that have qualitative similarities to this Bayes optimal boundary. So this is very interesting. I want to ask maybe a surprising question, or a bit random question, let's say. What happens if we rotate our data? So what I'm literally going to do is I'm going to take all of our training points, I'm going to rotate them in the x1, x2 plane, and I'm going to retrain our models on the rotated data. Okay, so it's a very small rotation. I've rotated by gamma, like some small fraction of pi radians. And I've applied it uniformly to all of our data points. And what's happened? If we look at that pink line, you can kind of see like the pink line has rotated about gamma radians. So it's moved smoothly with our data, as has the Bayes optimal decision boundary. But what's happened with the decision boundary that Adam is learning, right? Like before, we had this reasonable nonlinear decision boundary. Suddenly now, we have a linear decision boundary, and I'd say a very bad linear decision boundary. Like this is not, if I asked you to come up here with a marker and draw some line that separates, the clusters, I don't think anybody in this room would say, yes, this is the perfect line, right? Like it's certainly misclassifying a much larger proportion of the training data than any of the other rules. And it turns out like I've not, cherry picked this rotation for you guys. So here I'm repeating this experiment at a whole bunch of different angles gamma. I'm retraining my classifiers every time. And we see that, first of all, Adam is learning these linear decision boundaries that are constant for wide ranges of these rotation angles. And it's actually nonlinear for a fairly small fraction of angles, right? Like, let me see if I can rewind. Let's go maybe back to 0. And as soon as we click to like 0.02 pi and then slightly over, we're very quickly collapsing to a linear boundary. Yeah.
Just a quick question about SignGD. Is there any effect of a step size here?
Great question. Like in this example, great question. So I think the answer is, as long as the step size is sufficiently small, we'll see this behavior. I don't know what would happen if we pushed our step size to infinity. Like it could be that we could find an unstable regime where the boundary is changing a lot.
When it goes to 0.
Certainly when it goes to 0, it's provably converging to this kind of linear boundary for sign gradient descent. Okay. Yeah, I'm sorry. I'm so sorry. Were you asking about gradient descent or sign?
No, sign gradient descent.
I'm so sorry. Then I misspoke. For sign gradient descent, this is independent of step size. We'll see some theorems that make this formal.
Okay.
Yeah. Okay. So we've kind of identified two things that are changing very suddenly when we apply these functions. First, we're having a qualitative change in our decision boundary, namely from nonlinear to linear decision boundary. And then this is further having an impact on our generalization, since we seem to be learning the same linear decision boundary for a wide range of angles. So to me, this raises several natural questions. First of all, why is this happening? This seems like very undesirable behavior to me. Like, this is not a sensitivity that I would expect or want from my optimization algorithms. A second question is, like, how sensitive exactly are these algorithms? And then third, can we correct this sensitivity? Like, maybe what we might really hope to achieve is we'd like to get an algorithm that learns these nice long nonlinear boundaries and rotates smoothly data. So these would be our goals. Any questions before we dive in? Okay. So to understand why this is happening, let's first give a precise definition of these adaptive optimizers. So these are a very popular family, including Adam, which we've already mentioned, and Adam W. And these two have become like the default method for training massive neural networks. Like, if you go to NVIDIA's blog and you read their articles giving you advice on how to train your own copy of ChatGPT, they will tell you to use Adam W. So this is like a massively impactful optimizer. But there are also lots of other optimizers in this family that you may have heard of: Adagrad, RMS prop, and if an optimizer has come out in the past 15 years and it uses this Ada prefix, it likely belongs to this family. So this family all share what are called adaptive coordinate-wise learning rates. So to understand what this means, let's look at the update rule for Adagrad. So if we consider the update for the ith coordinate of our parameter vector, Adagrad takes a step that looks a lot like gradient descent. So we have our current position, theta sub t, taking our ith coordinate. We subtract off some step size times the ith entry of the gradient at our current iterate. But all of the difference is kind of wrapped up in this step size. So this is not a fixed step size, or even a step size that depends just on iteration number t, like we might use in gradient descent. This step size is also a function of our coordinate entry. And as we can see here in this expression, it depends on the previous iterates in our trajectory. And it turns out that the way that these coordinate-wise step sizes are defined make these algorithms non-equivariant. So what I mean by this is, if we took our parameter vector theta and we represented it in a different basis, we could get different solutions when we train using an adaptive algorithm. I want to make this very precise, since this is kind of a core point in this talk. So let's imagine taking an orthogonal matrix V that's a D by D matrix, and let's consider two different optimization problems. In the first, we just minimize like whatever loss function we have. And in the second, we minimize this loss function that we apply first to our parameter vector, this orthogonal transformation, and then we pass the result to our loss function. So mathematically, these two problems are very, very similar, right? Like, V is orthogonal, so there's no stretching or rescaling of any directions in our parameter space. These two functions have the same minimum values. Their minimizers are equivalent up to rotation. If applicable, they'll have the same Lipschitz, smoothness, strong convexity parameters as defined with respect to the Euclidean norm. Yet, despite the fact that they share all of these properties, if we use an adaptive algorithm, we can get different solutions. So this is what I mean by like these algorithms are non-equivariant. But if you're with me so far, you might say, hold on, Adela, like, you seem to be doing something a little bit apples to oranges. When you showed me this video of the red and blue dots, you were doing rotations in the x1, x2 plane. But now when you talk about applying V, to parameters, here you're talking about rotations in parameter space. So what's going on? The answer is that for many of our contemporary neural network architectures, there's a formal equivalence between rotations in data space and rotations in parameter space. So to understand that, let's look at this theorem. So we're going to consider any feed-forward neural network, and we're going to consider two-dimensional data X, like we had in our little cartoon. For any rotation angle gamma, we can define the 2 by 2 rotation matrix whose action literally rotates our data vector in the x1, x2 plane. Now, for any rotation angle, there exists some Q of gamma, a D by D orthogonal matrix, such that the neural network forward map applied to a piece of rotated data is equivalent to considering the neural network forward map at a rotated set of parameters and unrotated piece of data. So this is a formal way of saying for every rotation in data space, there is an equivalent different rotation in parameter space. And because we have this equivalence, now the fact that we've just talked about how adaptive algorithms are sensitive to rotations in parameter space means that they inherit sensitivity to rotations in data space because of this equivalence. So I want to make a brief comment that while we looked at this lemma in 2D, this is like a fairly general result. So like it doesn't matter what dimension our data is in, this holds. And then this statement also applies to like a wide class of neural networks. So like any activation, any number of layers, and this result subsumes other like reasonable modern architectures like CNNs or ResNets with trainable skip connections. So this equivalence between data space and parameter space rotations, shows up in many modern settings. Okay, so this answers our first question for us. Why is this happening? Well, these algorithms are not equivariant to rotations in parameter space, and rotations in parameter space have a correspondence to rotations in data space. Okay, so our next question, how sensitive are these algorithms? And I propose to formalize.
Well, is it as simple as just the input, the very first layer? If you're rotating data space, you just have the
Exactly. Yeah, like you have to do, there's a little bit of Kronecker product factorization. So like the rotation on the weight matrix is like an identity Kronecker producted with that data rotation.
Right.
But exactly. And then everything in the higher layers goes through. And if you have a ResNet, you have to do this with your skip connection weights.
Good.
But yeah, it's a very simple proof. So when we ask how sensitive these algorithms are, one way that we can formalize this is by asking, what's the smallest value of gamma for which we can obtain such a drastic change in our behavior? Okay, so before I present like our result, I want to set up the algorithms that we'll consider. So Adam has a very complex dependency on its trajectory history through like a momentum and an averaging term. So I'm going to actually analyze a very specific hyperparameter setting for Adam. I'm going to set a bunch of parameters equal to 0. This choice makes Adam memoryless, and it actually reduces to a different optimization algorithm called SignGD. So the SignGD update, we take our current position, we subtract off a fixed scalar step size times the sign of the gradient vector. So this will be a vector of +1s, -1s, and 0s. All right. Empirically, I'll comment that we do see strong agreement between Adam using default parameters and SignGD in our experiments, but still, I'm going to restrain myself to analyzing SignGD. So what can we prove? Yeah.
Yeah, I wonder, like, if your step size does not change, then at each step, your parameter will be moved by a fixed distance, right?
Yes.
So does this algorithm even converge?
Right. So depends. Like in our examples, we'll see that the decision boundary converges, even though the parameters themselves may be changing.
I see.
Yeah. Great question. Okay. So what can we prove? So we have the following result. First, let's think about any non-zero and non-trivial rotation angle gamma. Then I claim there exists a distribution such that the following two results hold simultaneously. So the first result comes from this manuscript that we mentioned before. They prove that training with sign gradient descent on this data distribution CalD will produce a nonlinear decision boundary. And so I've illustrated this with this top right cartoon. This is an example of this reasonable nonlinear decision boundary. Then we prove that if we train the same network using the same algorithm on a distribution CalD that's identical but rotated by this arbitrary, like this small gamma, we will provably learn the following linear decision boundary. We're going to learn a decision boundary that corresponds to vectors such that x1 equals -x2, which is exactly this linear decision boundary that we're seeing over here. So taken together, our result and Vasudeva's result imply this arbitrary sensitivity of adaptive algorithms. If you come to me with a non-zero gamma, no matter how small, I can cook up some distribution such that when I train on the unrotated data, I get one set of behavior. And when I train on the rotated data, suddenly I collapse to learning this exact linear boundary. So this was surprising to me. I want to give you guys like a small kind of flavor of how we prove this. What we do is we characterize the weights that you learn when you're training with sign gradient descent. So we fix any outer layer weights, any step size, and we'll use WT to denote the weight matrix learned by sign GD after T iterations of training. And then we show that for any rotation angle that's non-zero, there exists some distribution such that the weights that you learn are the following. If you look at the kth row of the weight matrix, so these are like the weights corresponding to the kth hidden neuron, we're going to consider the unit vector in that direction. So I'm ignoring the magnitude of that weight vector, and I'm just considering which direction it points in. Then this vector will evolve to be parallel to basically the 1, 1 vector, where the sign is determined by the sign of your outer layer weight. So you'll either evolve to be parallel to 1, 1 or to -1, -1. And what I'm plotting here are some snapshots of our weights during training to kind of validate this prediction. So at initialization, like all of our weights are kind of uniformly scattered around the unit circle in direction. After 10 epochs of training, we have that all of the weights whose outer layer weight is negative have collected in this half space. Almost all of the weights whose outer layer weight is positive have collected up here with a few stragglers. And if we train for another 200 epochs, they collapse to almost point masses exactly where we predict. So this says that, first of all, our theory is holding up when I run my experiments. And then second, even though this is an asymptotic result, it's kicking in fairly quickly. And the punchline here is that once you've characterized the directions that these weights will evolve to, you can compute what that decision boundary will result in. And so this is how we obtain this linear decision boundary. I want to comment that our theory is still predictive when we relax some of the strong simplifying assumptions that we make. So in particular, all of these weight snapshots and this linear decision boundary that I'm plotting, I got when I trained a network that had, first of all, trainable outer layer weights, trainable biased terms, and then I was using Atom with its default parameters, not just sign GD. So even though we have to design our analysis in this very restrictive setting, our theory is predictive when we relax these assumptions, which is nice. Okay. So this answers our second question, how sensitive are these algorithms? Well, we prove this existence result. For any arbitrarily small but non-zero angle, there exists a distribution where your rotation will have a significant impact. This to me, again, kind of a problem. I don't want to use an algorithm where an arbitrarily small rotation can drastically change my outcome. So can we correct this sensitivity? Quick spoiler alert, we will see that there is some method that does this. So on the left, I'm plotting this same video that we've seen several times with the traditional algorithms. And on the right, I'm using some mystery method to augment these algorithms. And if I can get this to play, we see that what we get using this mystery method is exactly what we desired, right? Atom is learning a nonlinear boundary close to the Bayes optimal decision rule, and it's rotating smoothly with the data. So what is this mystery method? Yeah.
So, in the visualizations and experiments, we're in input dimension 2.
Yes.
Tons of data.
Yes.
But in any normal network problem where we have lots of data, but tons of dimension.
Right.
And, the number of directions grows exponentially with dimensions,
Uh-huh.
right? So I guess I'm curious about whether the theory and analysis you were discussing is just for D equal 2, or it generalizes to arbitrary directions, and how that relates to data density in that space?
Great question. Okay, so first, part of our theory about this equivalence of rotations in data space and rotations in parameter space, fully general. Doesn't depend on our, generalizes to any data dimension, and it's independent of the density. Okay, the second result It's an interesting question. Like, could I prove this if instead of considering the population loss, instead of considering the expected loss, I take the population loss and I restrict myself to a setting where I have like fewer sample set dimensions.
Or even just, because again, I mean, think about how many versions we have in hypercube in dimensions. There's 2 to the 2, right?
Correct.
Somehow the number of directions really grows fast.
Yeah.
And even if you still have lots of data, it's almost an empty space, right?
Right. So to be honest, I'm not sure whether you could construct one of these like arbitrary sensitivity examples in this setting. I feel like though this is almost like saying, even if we were in this, very nice case where we have tons of data, which is unrealistic, like that this sensitivity is not an artifact of that limited samples. Let me turn the audio on, and then we still have these settings selected. Okay, so hopefully Zoom people can still hear us. Sorry about that. All right. Okay. Hopefully all good now. We'll see if Eduroam tolerates us. Okay. So what I'd like to do now is give us the setup in order to tell you guys about what this method I'm using to remove this sensitivity is. So to do this, let me first introduce some notation. So we're going to consider like a typical optimization problem where we have some loss function that maps from RD to R. And our task generically is to find a minimizer of this loss function. Something that we've already talked about in this talk is the impact of orthonormal reparameterization. But just to reiterate what this means is we have some D by D orthogonal matrix, and we define a new loss function, L tilde, by composing our loss with our orthogonal matrix. And because V is orthogonal, what this does is it literally rotates our whole loss landscape about the origin, no rescaling or stretching in any direction. Okay, so if we look at the original Adagrad papers, the authors were motivated by settings where the gradients were sparse or axis aligned. So what this means is if we look at the gradients, which I'm plotting here in red arrows, at different points in parameter space, we see that over here on the right-hand plot, at many points in parameter space, the gradients are approximately parallel to either the first or the second coordinate axis. And certainly that's more true over here than it is the left-hand plot. So we see that this right-hand plot has more axis-aligned gradients. And it turns out that reparameterizations, and particularly reparameterizations that make our gradients more axis-aligned, can significantly impact our convergence. So here I'm initializing Adagrad at these two upper right orange points that are equivalent up to rotation. And then I'm running Adagrad with identical hyperparameters. And we can see that Adagrad is taking completely different paths in these two settings, and it's also taking many fewer iterations to converge in our right-hand plot. So one question becomes, is there a systematic way to promote more axis-aligned gradients in our loss landscape? So to answer this question, we turn to the EGOP, or expected gradient outer product matrix. So if we have a loss function that maps from RD to R, then our EGOP is defined as the expectation over parameters theta of the gradient of the loss with respect to those optimization parameters outer producted with itself. So since our gradient will be a d-dimensional vector, this will give us a d by d matrix. This expectation is defined with respect to some user-specified distribution rho. For the sake of this talk, I'm going to think about rho isotropic. So one thing to keep in mind is like a Gaussian, where our covariance looks like sigma squared times the identity. The reason why we turn to the EGOP matrix is that its eigenvectors are known to capture what are called the primary directions of variation in the function. So what I mean by this is, in this little loss landscape that I'm plotting here, in red, I'm plotting the leading EGOP eigenvector, which points in this direction. And you might be able to see that this leading eigenvector points in the direction of the one-dimensional subspace, where this function is varying most sharply in this region. And so as a result, if we think about capital V, the eigenbasis of the EGOP matrix, and we consider reparameterizing by the EGOP eigenbasis, we're going to make that leading primary direction of variation into the first coordinate axis, first coordinate basis element. And so hopefully this will promote more axis-aligned gradients. Like visually, the intuition is that here we can see that this valley now resembles kind of the right-hand plot that we saw previously with the blue striations, where most of our gradients are looking approximately parallel to either the first or second axis. Okay, so this suggests the following meta-algorithm. If you come to me with a loss function and you really want to optimize it using, say, Adam, I could say, okay, first, let's use Monte Carlo sampling to estimate the EGOP matrix. Let's either compute or estimate its eigenbasis, V. And then let's reparameterize. So let's form L tilde by composing L with our orthonormal matrix V, and we'll optimize L tilde instead. And the hope is that this will improve our convergence. So before we dive into the convergence guarantees, are there any questions about like this algorithm or the method that we're considering? Yeah.
This is super naive, but is this thing related to the Fisher information matrix at all?
Great question. Yeah, so the Fisher information matrix also has some similarities. But with the Fisher matrix, so first of all, for those of you who haven't seen it before, the Fisher matrix, we're usually thinking about the gradient of the score function or of the log density. And we're also thinking about, for the Fisher, the expectation over data. So here we're thinking about, right, like this is just defined with respect to any parameters theta. We haven't even necessarily got a loss function that explicitly depends on any kind of data. So if we had a Fisher matrix instead, we would have like L, a function of theta and X, and we consider some expectation over X. So like I think they have a relationship, and I think in general, kind of the relationship between the data and parameter expectations is something that I'm interested in, but they're not quite identical here.
True.
Okay, so let's see what we can prove about this algorithm. So I'm going to make some simplifying assumptions. So let's consider a convex loss function constrained to some ball. And then I'm going to assume that the Hessian of this function is Lipschitz within our constraint set with a sufficiently small Lipschitz constant. And so the right intuition here is that we're asking that the curvature of our loss function changes sufficiently slowly within our constraint set. So if we make these assumptions, then after we optimize with Adagrad for t iterations, we can bound the regret in original coordinates by some function r that depends on L, our loss function, our step size, our constraint set, and our number of iterations. I want to black box this original coordinates regret bound and just compare it to the regret that we get under EGOP reparameterization. So first, what we have showing up is the same function r with the same inputs. So these two will literally always spit out the exact same value. But these two regret bounds differ by this factor in yellow. So in the numerator of this factor is what's called the stable rank of our loss. So the stable rank is defined as the sum from I equals 1 to d of the square root of the ith EGOP eigenvalue normalized by the leading EGOP eigenvalue. So what this does is it measures the level of spectral decay that we have in our EGOP matrix. So to run like a quick sanity check, in one extreme case, when our EGOP is rank 1, we would have exactly one non-zero eigenvalue, lambda 1. So we'd have square root of lambda 1 divided by lambda 1. The stable rank would be 1. In the other extreme case, EGOP has all like exactly equal eigenvalues. then we'd have d times square root lambda 1 divided by square root lambda 1. So we'd have d. So the upshot is that this factor here in yellow can be as small as 1 over d and as large as 1. So this is like a savings factor. And in fact, this savings factor gets more extreme when we're in cases where this stable rank is much smaller than dr ambient dimension. And this is exciting to me because I claim that this condition, small stable rank compared to dimension, is actually fairly widespread in machine learning. So to give you guys an example, here I'm plotting the eigenvalues of the EGOP matrix for a 2-layer ReLU network with images of handwritten numeric digits. So what I'm plotting on the y-axis is the ratio of lambda k over lambda 1, and I'm plotting this for all k of our eigenvalues. And we can see, like zooming in on this linear inset, that these eigenvalues decay quite sharply. As a result here, the stable rank of this EGOP matrix is much, much smaller than the ambient dimension, which is like over 2000 in this setting. And I hypothesize that this is actually a fairly widespread phenomenon. Certainly, if you fix your loss function and you fix your network architecture, you can prove that like a low-rank structure in your training data induces low-rank structure in your EGOP matrix for some loss functions. And more generally, we've seen a lot of empirical work documenting that data sets in machine learning may have some intrinsic low-dimensional structure or tend to have much smaller dimension than their like ambient space. So like I'm very excited about this because this suggests that for many machine learning problems, we may be in a regime when EGOP reparameterization could potentially significantly improve our convergence guarantees. Okay, so these were all like, theoretical statements, but how does this play out in practice when we apply it to some nasty non-convex, machine learning objective? So here, I'm plotting the training loss over epochs for training some ReLU network to classify images of digits. I'm using solid traces to plot the performance of algorithms in original coordinates and dashed lines to plot the performance under EGOP reparameterization. And we can clearly see that for the adaptive methods, namely Adagrad and Adam, reparameterization is significantly impacting our convergence, right? The EGOP reparameterized variants are converging to lower training loss in fewer epochs. And this is kind of a broad statement that we've observed in like a variety of different machine learning experimental setups. So I'd like to give you guys a couple quick vignettes of what I think are some of our most compelling experimental results. And to do this, I want to quickly introduce some state-of-the-art baselines. So you guys may or may not have heard of two algorithms called SOAP and Shampoo. Very cute names. Shampoo was named, to quote the authors, because it has to do with preconditioning, which I think is a delightful pun. So this is our little dog being shampooed so that we can all remember that pun. So Shampoo is uses a preconditioner that has a product for product structure. And people were very excited about Shampoo because it performed very competitively in some large-scale benchmark experiments. SOAP is a more recent variant that was proposed to carry out some of the updates that Shampoo performs in more efficient ways. And the reason why I've chosen these two, modern optimizers to compare with is that they share some conceptual similarities with EGOP reparameterization. So in particular, the preconditioners that SOAP and Shampoo use both use some kind of spectral information of a certain notion of a gradient covariance. But as I mentioned, SOAP and Shampoo use a preconditioner that's constrained to have a specific Kronecker product form. Whereas EGOP reparameterization, so far we haven't imposed that kind of constraint. So let's see how we, perform compared to these guys. So in our first example, I want to consider low-rank matrix factorization. You guys may be familiar with this objective, but basically we're going to optimize over these factors L and R to try to match some unknown ground truth rank R matrix. And what's notable about this problem is that the block Hessians, the Hessians with respect to the parameters of L and with respect to the parameters of R, both admit exact Kronecker product decompositions. So in theory, this is a problem where the structure is well suited to the constraints imposed by SOAP and Shampoo. And the surprising result was that EGOP reparameterization is nonetheless much more effective at optimizing this objective. So here I'm plotting our loss function versus iterations. And we can see that in the solid traces here we have soap, shampoo, and original Adagrad and atom. And in the dash traces, we have the EGOP reparameterized versions, which are converging more quickly and achieving lower ground truth reconstruction loss. More generally, EGOP reparameterization is targeting a different kind of structure than soap and shampoo. We're targeting this like EGOP spectral decay, whereas soap and shampoo target this Kronecker product structure. So this is a little example showing that, as we move from problems with good Kronecker product structure to more poor Kronecker product structure, soap and shampoo struggle to adapt. So like these traces up here where soap and shampoo are converging more slowly, they have worse Kronecker product structure, whereas the EGOP reparameterized atom traces are all converging basically at the same rate, independent of this Kronecker product structure. Lastly, I want to comment that, my excellent master's students, Rick and Jose, put in a lot of work to help me scale this to large-scale problems. So here, I'm showing results from training a deep residual network on ImageNet, and we can scale EGOP reparameterization to perform competitively here. So I'm considering an additional variant where instead of just computing our EGOP eigenbasis one time upfront, which is what we've considered at every point up to this point in the talk, now I'm periodically recomputing my EGOP reparameterization. So I'm doing this k times per epoch. And we see that when I run EGOP reparameterization, where I reparameterize once per epoch, we converge competitively in like training loss versus epochs, and in wall clock time, we're quite successfully minimizing the converging to low validation loss efficiently. So this was exciting to me, that we can offer a benefit in these massive problems that are really kind of the interest place applying adaptive optimization algorithms. Okay, so that was all about improving the convergence of our algorithms. But what about our original question about these data rotations and their generalization? So basically, we can prove that EGOP reparameterized algorithms are equivariant to orthonormal transformations of our data. And this includes data rotations. And while I, encourage you guys to check out the formal statement in our paper, I think this video kind of captures the informal result quite clearly. When you train using an EGOP reparameterized algorithm, the result that you get will transform smoothly as you rotate your data. So we've gotten rid of that sensitivity that we were worried about. Okay, so this kind of closes the three questions that we've posed, at least some parts of these questions. Zooming out real quick, just to recap, the punchline of this work has been that the non-equivariance of adaptive optimizers means that they can be very sensitive to both rotations in data and parameter space. We saw that for our common choices of neural network architectures, there's an equivalence between rotations in data space and rotations in parameter space, which means that as a result, these popular algorithms can be highly sensitive to data rotations. And we saw that reparameterization is one way to alleviate this sensitivity. And then we saw that when we have low dimensional structure in our data, which can induce strong EGOP spectral decay, EGOP reparameterization offers one way to potentially improve the convergence of our adaptive algorithms. Okay. I want to briefly comment on some of the future directions that I'm most excited about. First, we saw good performance of the EGOP reparameterized algorithms in our little red and blue dots vignette, but we didn't actually analyze or prove anything about the solutions they would converge to. So it'd be interesting to me to analyze the implicit bias of these optimizers in the EGOP eigenbasis. I'd also be interested in the impact of other kinds of seemingly benign transformations on the performance of adaptive algorithms. So in scientific applications of machine learning, we often have to make some choice about a function basis or a discretization that we think of, as not having a huge impact on our problem. And it would be interesting to understand how adaptive algorithms respond to these different choices and whether we can improve their performance by promoting equivariance. I'm also interested in analyzing some of these modern preconditioning algorithms, like we mentioned soap and shampoo. And we do have partial results in this direction. So our analysis of EGOP reparameterization and our proof that it makes these algorithms equivariant, extends to soap and shampoo. So this may be part of these algorithms' success. And then lastly, I'm quite interested in how rotations, reparameterization, and more broadly our choice of optimizer impact feature learning. So at a high level, feature learning refers to the tendency of neural networks to automatically extract important geometric facts about your problem, potentially by encoding them in your weights. The analysis that we did, kind of characterizing the weight trajectories learned, already shows that rotations can have drastic impacts on your feature learning. But I think it would be really exciting to develop a more robust understanding of how different different optimizer choices impact feature learning in neural networks in practice. So with that, I want to thank you guys. I'd be happy to take your questions. And also, if you check out our papers offline and have questions that you'd like to pose over email, I'd be happy to receive your emails. So thank you.
Well, we've got time for a few questions, so got some burning questions. Go.
Oh, great talk. How would you choose distribution of the parameters?
Great question. Okay, so let me rewind real quick so that I can show everybody. I think you're asking about this distribution here, rho, right? Okay, great question. So first of all, in practice, what I've done is I've often chosen rho to be the initialization distribution that we use for the neural network. So a lot of work has gone into designing good initialization distributions. And so when I estimate my EGOP matrix, I just draw a bunch of those. In other problems, I usually just use some standard Gaussian. And I've done some experiments showing that when I change the scale of that Gaussian, it doesn't have too much of an impact actually on the eigenvectors that I learned for the EGOP matrix. So
and then sorry, just to follow up, and then when you reparameterize, how does that, when you do it sort of around the local?
Exactly. What I do is I use the same distribution rho, just so I change its mean and I make its mean our most recent iterate. Exactly.
Okay. You go.
Oh yeah. So have you measured how much that changes throughout training? You say that you sometimes reconstruct the EGOP basis, but it's say it's even though it would take a while, even if you did it, say it's every many times in epoch, does that greatly increase the convergence?
That's a good question. I think for our example with the ResNet, the answer is no. Reparameterizing once per epoch versus boosting this to maybe maybe a couple dozen times per epoch, I didn't see a big difference. There's already the thing that's kind of surprising to me, doing the one-time upfront reparameterization is already fairly similar to doing the periodic reparameterization. I was kind of surprised in our other examples, even with this tiny MNIST network, I was expecting that to get this to work at all in any neural network would require lots of periodically recomputing this basis. But no, I haven't it would be fun to run some experiments where I look at the angles and the changes in these eigenvectors and really quantify how much heterogeneity there is.
Steve, else?
Do you want to follow up?
Well, no, but
Let's put one over here first. Yeah, go ahead.
just making sure to see.
Yeah, I was wondering, how does your method scale with?
Yeah.
Because I am assuming the other ones which assume the chronicle structure do so because very hard.
Exactly.
To store and manipulate a
massive matrix, right? Yeah, absolutely. So to scale this to this massive ResNet, we have to implement a bunch of computational heuristics. One of the short summary statements that I can make is that it turns out that it really only matters that you get an accurate estimate of the leading EGOP eigenvectors. Most of the trailing eigenspace isn't actually capturing that much important information. So we can save a lot of compute, first of all, by using randomized techniques to only estimate these leading ones. And then second, when we have massive and deep neural networks, we're actually restricting to some layer-wise and then parameter chunk-wise implementations. So here, soap and shampoo are computing different preconditioners for each layer, and we're mimicking that structure. And we're using some facts about the shared geometry of for example, the convolutional filters to also save on memory. So you're completely right that massively scaling, kind of the naive EGOP reparameterization that we showed in this meta algorithm, quickly hits in costly memory constraints. But when we implement these heuristics to try to mitigate that, we see that we're still getting like fairly good success. Yeah, great question.
Okay, one more from Beck.
Yeah, thanks. I had a question about relationship of this to the geometry of the function.
Yeah.
Sense. When I, a few years ago, reading the papers on like sin GT, sin SGT.
Yeah.
A lot of them like were proving like, oh, if you take a step size to 0, you get the stationary point of the same, loss functions.
Mm-hmm.
So I guess if I assume if there's only one stationary point, sin GD would get the same stationary point as normal gradient descent.
Right.
If you have many, there's some bias like that happens. That my line, like this, geometry of the loss, meaning like number of stationary points and so on, relate to the.
This is a good
fact that you're getting different solutions.
Right. It's a good question and hard to answer in general. One thing I guess that I'll say is like, for example, if you assume that you have some linearly separable data, then there are stronger results analyzing what sin GD will learn. And you can prove that the solution that you converge to will always be an L infinity margin maximizer. So like there is still some control even when you have multiple stationarity points. Here we're in a setting where we don't even have separability. I don't really have a good intuition other than like to echo that exactly like you said. If we had a single point, we'd be converging to the same solution if our step size is sufficient. But yeah, good question.
All right, we're going to wrap it up here. So let's thank Adela. And to come and chat.